Hello guys, welcome again on my music modeling channel. Sorry for a big delay, I'm solving some problems in my real life now, but next video will come faster and actually I will improve the quality of my setup from video to video. In the first lecture I will cover some basic definitions which you will need to take into account when implementing your own musical model. So you just cannot get away from it. Let's start with a simple thing. What is a node? At first I will give a simplified definition of the node because it can be extended. So let's start with simple things. A node is a certain sound of a certain duration and pitch. I use short names for these things, as later on in my coding sessions you will see all these variables. Actually, this is quite simple, yes, but later we can extend this thing with position of the note, of the volume, and of the instrument. Actually, now you may ask why do not we take into account the position of the note, but at first we assume that there are no pauses, so each note comes one after another, so we just are enough with durations currently. And pitches, of course. So let's now, on a simple example, show how these quantities are encoded into machine. Here I have drawn three nodes. Here two of length 1 and third of length 2 quarters. I mean, this Q stands for the quarter, and you see that they are positioned on the node lines. If we measure the durations and pitches in, let's say, normal musical system, we can say that they have duration of 1 quarter or 2 quarters and certain pitches like G of the 4th octave or something like that. But that is actually not really suitable for computer. It's not really uniform representation. So let's proceed in rewriting that in a more formal way. Let's first define a duration quant. It is a minimum duration which we take into account in our model. Also, we will need a meter, and then we define what is a measure or a tact. Let me make a small remark that I'm a Russian, Ukrainian speaker, and our terminology is a little different. So if you will face some non-correct terms here, so that comes from that side. So sometimes I will use the word tact, and occasionally so I use also T here. So tact is a measure. Then we can see that the positions here also can be drawn. It's quite obvious for this case, but yeah, it doesn't actually matter. So for the simple case, let's just start with the smallest node as 1/64. So we call it the minimum quant of our duration, and then if we take that meter is full meter 4 times 4, then we can say that it's actually 64 times 64. So we are measuring our meter in our duration quants. And then a tact is a collection of the nodes which start at positions like 0, 64, 128, or other just numbers of this meter length. And the sum of the duration of all the nodes in the measure equals to meter. That's obvious. Let's now show representation here. So if we consider that pitch of the note C0 is 0, and then when we just go 1/2 tone or semitone above, then we increase this number by 1. So C1 will have number 12, C2, number 24, and so on. So then we have this numerical representation for pitches and also for durations. We now can nicely measure it in our smallest dq duration quants. Now let's talk about pitch, how it is defined physically, and how do we encode it within computer. So a pure pitch is a sinusoidal oscillation of pressure. It's a sound wave, and across its way where it's propagating, it creates zones of positive and negative pressure, which you can see on this plot. If you fix a point in space and just measure the pressure over the time, you will also have this sinusoidal shape. I'm sorry that on the left it's a little cut, but the magnitude of these oscillations is called an amplitude. Sometimes you call half magnitude of this as an amplitude, but nevertheless. And the volume, which is a human perceived quantity, is actually proportion to the logarithm of this amplitude. Later on we will see similar thing with pitches, which reflects a proverb by some ancient scientists who said nature loves logarithm. And what about pitch? At first we have here a time period. A period is a time span after which each value repeats itself exactly. So two peaks are separated by time period. And then pitch is actually inverse value for this period. It tells you how many oscillations does the sound wave make in 1 second. Let's expand a little this definition. So, as ancient Greeks or even people before them noticed, if you have two exact strings, one is of double length compared to another, they will have pitches which are different exactly in 2 times. The shorter string will have higher pitch. And when two pitches are exactly 2 times apart, this is a perfect interval called octave. This way, octave is a doubled pitch. And in modern Western music, the mostly used system is so-called equally temperate scale, which divides the octave into 12 identical intervals in a logarithmic scale, which means the two pitches which are separated by 1 semitone will always have pitch relations with 2 to power 1 to 12, which is actually a 12 power root of the number 2. Okay, and what can we do with that? We know that C of 0 octave has a certain pitch of 16.35 Hertz, which is 16.35 inverse seconds. C sharp of the same octave will have a pitch this times higher, and then you can go up to whatever note you want. Now let's do some small theoretical retrospective and speak about perfect intervals, consonant intervals. These intervals are the ones which sound pleasant to our ears, and they were defined by Pythagoras, and as the intervals whose pitches are related to each other as the simple numbers. The most perfect interval is octave, when the pitches are doubled against each other. Of course, we have prime, but it is a trivial case where two pitches coincide. We also have quintet quad, which are perfect fifth and perfect fourth. They are two subsequent most perfect intervals, and they are defined by Pythagoras as 3 to 2 and 4 to 3 relation, kind of the simplest simple number relations that you can have here. And in our equally temperate scale or a system of measurement, we have the same intervals defined in the semitones. Let's say octave has 12 semitones, perfect fifth 7, perfect fourth 5. And then if we calculate the actual pitch relation based on this semitones definition, we will see that these pitch relations are not really coincide with their perfect definitions. And this actually leads to some imprecision in instruments tuning. Actually, every instrument which you can find around yourself is tuned imprecisely if we refer to perfect quint, quart, and other intervals definitions. This difference is even more prominent for small and minor and major thirds, and you can calculate that yourself how much is it different. Now let's go to the durations, but how do we calculate that? You probably heard such quantity as BPM, beats per minute, which is actually a number of quarter notes per 60 seconds. Quarter note would be 1/4 for the full meter, but of course that's not actually the case. We can have BPMs for any meter, but the quarter note stays here. So how can we transform our BPM to our actual duration? I will show you some formulas here which are pretty universal and are pretty trivial. So if you have a 4x4 meter, which is actually 64 times dq, which is our duration quant, then we have a bit duration as 1/4 of this, which is actually 16 times dq. And to make 16 bits, to make a BPM number of bits, we need 60 seconds. So actually, you see this formula, and from this you can derive dq value for the 4x4 meter. For a more general case, you can just have here your meter divided by 4. So for this formula, you now can define your smallest note duration, and based on that, you can have all other notes duration precisely defined. Now we are approaching the end of the presentation, so let me give you 2 tasks which you can do yourself and check. At first is by how much minor and major thirds are differ from their ideal Pythagorean definitions. And also another interesting task would be to calculate at which BPM the 64th note duration is less than 50 milliseconds. There is a so-called Haas effect, which tells us that our ear hears 2 sounds as one sound if they are separated by less than 50 milliseconds. Of course, this number is quite approximate as everything when it comes to even physics, not spoken about nature stuff and human perception. But still, this might be a good test just to check when you will stop distinguishing 64th notes from each other. Next, we will talk about designing measures, which is a next structural unit on top of the note. We'll talk about rhythmic structure, about the melodic structure, the harmonic structure of measures, and the repetition patterns they follow. And for this, of course, we will extensively rely on the definitions we have defined in this lecture. See you in the next videos. Bye bye.